Hi guys. So we finished up a discussion last time with using the node voltage method in order to analyze with a circuit with a dependent source, and that was kind of a special case. However, there are other special cases which will lead you into trouble uh, in terms of circuits when dealing with the node. You're trying to use a node voltage method to solve, and that's the discussion for this next section. This is section 4.5. This is on special cases of circuits when using the node voltage method. And more importantly, this is on a new concept, that of a supernode. Now, there's kind of a big idea that underlies all of the techniques of circuit analysis that we've been developing up until now, right? And the big idea really is that we want, it's worth writing down. So let me do that. We want to set up systems of equations with the least number of variables. And the reasoning behind this should be pretty obvious. The more variables that you have in your system of equations, the more difficult it is going to be in order to solve that system. So in order to avoid defining more variables, we can actually use the concept of a supernode. So to avoid defining more variables for some circuits, we can use a supernode. Now let's go ahead and define what a supernode is and what to look out for, and I'll show you why it is that you need to look out for this. A supernode is used when using the node voltage method and only the node voltage method. So you can have circuits that you're using different methods to solve, and the supernode concept will play no part in the analysis whatsoever. And it's when a voltage source is between essential nodes. We combine the nodes to define a supernode. KCL must still hold for the supernode. So we'll define a supernode and we'll still use KCL there. One thing that's actually going to be very important, and you'll see where this comes in, it's something that tends to be overlooked quite easily from time to time. It's that once you use KCL at that supernode, after combining those two nodes, you must get a constraint equation by taking a look at the node voltages and the voltage source inside of the supernode. So you get a constraint equation by looking inside the supernode voltage source and the node voltages. Again, it's very easy to overlook that. So So in this particular case, the example that I have for you guys is the following. This is for the supernode. And quite simply, it's to find V naught in the circuit below. And the circuit contains an independent current source providing us with 2 amps down. It then is hooked up to a resistor here. There's an independent voltage source with that polarity that provides us with 25 volts. There's another resistor there, and then lastly, resistor there, and then the entire thing is connected. This is a 50 ohm resistor. This is a 150 ohm resistor. This is a 20 ohm resistor, a 55 ohm resistor, and lastly, the voltage V naught that we're looking for is the terminal voltage across the 50 ohm resistor. Now, suppose that we went ahead and started trying to use the node voltage method in order to analyze the circuit. First and foremost is we need to identify the nodes. So very clearly there's one very large node down here, like so. I already know that I'm going to choose this one as my ground. So I'm going to go ahead and say that this is the ground node and this has a node voltage of 0. There's another node there. There's another node here. And then there's one last node there. Right. Now that we've identified our nodes, we need to take a look at the voltage sources in order to start our labeling of our independent nodes. Now, notice that this node up here and this node voltage, or this terminal voltage, they're related in terms of the node voltages. In particular, if I start at the reference node and I go up like this, notice that I go through a voltage rise of V naught, so I don't need a separate variable name for the node voltage at that node. I can just say that this is the node voltage of V naught, because we've chosen this as our ground node. There is a voltage source here. Right. Now notice that that means that the voltage at this node and that node, they have to be related to one another. Right. In particular, the node voltage over here, because this is positive and this over here is negative, the one node voltage on that end must be bigger than the one at the other end. So here, immediately, we're going to be led to a constraint equation. But notice that we don't have a variable name for the node voltage there. So we need to define it. Suppose that I call this node A, I'll call this node B, I'll call this node voltage VB. Right? Now, there is another node, this one over here, but it's not an essential node, so we don't need to give that node voltage any sort of variable name. Right? So immediately, we have to come up with a constraint. And the constraint is, well, VB and V naught, right? Because the polarity is such that this is positive, this V naught must be bigger than VB. And it must be exactly bigger by 25 volts. So the constraint equation is that V naught is whatever VB is plus 25 volts. This equation right here, before we do any more analysis, is our very first equation. Next, what we need to do is we need to use KCL at nodes A and node B, because they are essential nodes, to start writing down a system of equations. Right? So let's go ahead and start doing that. And one of the things that you'll see is immediately we run into a problem, but we can overcome it. So here I'm going to use KCL at node A, and the version of KCL is the sum of the currents flowing out of this node must add up to 0. And let's actually take a look at that node. So here we have 2 amps flowing out. So we have plus 2. We have a current flowing from there to there, and that is plus V naught minus the ground node, so 0 volts, divided by the 50 ohm resistor, like this. And then we would want to say this node voltage minus this node voltage divided by the resistor that this is going through. But this is not a resistor. It's a voltage source. So we cannot use the modified version of Ohm's law in order to write down an equation for the current that happens to be flowing from this node out to that node. We cannot use it. Why? Again, because that is not a resistor. It is a voltage source. So one of the things that we can do is, when you don't know the value for something, is you can define it. So what's running us into trouble is we don't know the current through that 25 volt source. So I'm going to define it to flow this way. I'm going to say this is I of 25 volts, like this. So this right here is the current that's flowing from there to there. Now, you might be an astute student and say, well, you define it to go from here to there in that direction. Why didn't you define it to go in the opposite direction? Right? And the answer is you could have. You could define it to go in any direction you want. As long as you stay consistent, the mathematics will always work itself out. So I have chosen that current to flow out of node A through the 25 volt source out to node B. So into KCL goes plus I of 25 volts. Those are the only elements at that node. They must add up to 0. This is going to be my equation 2. And one thing that I really want to highlight is I needed to introduce this new variable in order to actually get that equation down. Right. Now, let's go on to the next essential node. So I'm going to use KCL at node B. So the sum of all of the currents flowing out of this node must add up to 0. So here we have at node B, we have a current going this way, a current going from there all the way down to the ground node through the 20 ohm and 55 ohm resistor. And we also have a current flowing into that node like so. So let's start with the first one, the simplest one. So first we have VB minus 0 volts through 150 ohms. That's this current. Then we have a current that's flowing through, notice that this resistor and that resistor are in series. They go from VB all the way down to the ground node, flowing through the series sum of the 20 plus the 55 ohm resistor. So we have plus VB minus 0 volts, and it is the series sum of the 20 plus 55 ohm resistors. And then lastly, we have this I of 25 flowing in to the node, which means flowing out of it, we have minus I of 25 volts. That is equal to 0. This is going to be my equation 3. Now, let's take inventory very quickly in terms of what it is that we have and our variables. Notice that what we actually have here is our unknowns. Well, we don't know V naught. We don't know VB. That's there, that's there, that's there, that's there. And lastly, we also don't know I of 25 volts. That's there, and that's there. So here, just going systematically through our equations and writing down our unknowns, we have 3 unknowns, which means we need 3 independent equations. We have equations 1, 2, and 3. It's possible to algebraically solve for everything. So 3 equations, 3 unknowns, we're good to go. Now I'm going to go ahead and keep those in my back pocket, right? And I'm going to go back up to the circuit, and I'm going to go ahead and define a supernode. So I'm going to rewrite the circuit, redraw it, so that we can actually do this. So that we're going to do this using a supernode. So we still have our independent current source providing us with 2 amps. Whoops. Then we have a resistor down this way. We have our independent voltage source providing us with 25 volts. Resistor down this way. Resistor that way. Resistor that way. And then everything is complete. V naught is still there. This is a 50 ohm resistor. This is 150 ohms, 20 ohms, and then 55 ohms. So we're going to do the same thing that we did previously. We still need to identify all our nodes. They're the same ones that we identified previously, like so. And then we have our ground node right there. Now notice that we can actually combine these 2 nodes into one big supernode because they meet the criteria for supernode. Remember the criteria. When a voltage source is between essential nodes, we combine the 2 nodes to define a supernode. KCL must still hold for that supernode. So right here, what I'm going to do is I'm going to circle both of these nodes, and I'm going to call this a supernode. Right? And I avoid kind of dealing with what's inside of the supernode for now. But I can now use KCL at the supernode, and the sum of the currents flowing out of this supernode must add up to 0. So out of the supernode, we have this current flowing out, so we have plus 2 amps. We then have current flowing from there to there, and that current is, remember that this, with this as my ground node, this node is at node voltage V naught, so we have plus V naught minus 0 volts divided by the 50 ohms. Then we have, well, we need to give this a label, so I'll call this node B. This is VB, like this, just like we had previously. And that current flowing down that way is VB minus the ground node over 150 ohms. And then lastly, we have a current flowing out of the supernode that goes like that, and that is VB minus the ground node divided by the series sum of 20 plus 55 ohms, and that must add up to 0. So in terms of all of the currents flowing out of the supernode, notice that we have a total of 4 of these currents. Right? So this current is flowing out of the supernode like this. This current is flowing out of the supernode like that. This current is flowing out of the supernode down like that. And then lastly, this current is flowing out of the supernode down to the ground node like that. So we added up all of the currents flowing out of that supernode. notice that this equation does actually contain two unknowns. We still don't know V naught and we still don't know VB, but we can actually get our constraint equation. Remember what I put in stars? The constraint equation is obtained by looking inside the supernode and taking a look at the voltage source as well as the node voltages. So just like before, we do have a constraint equation. This is equation 4. So we have constraint equation by looking inside or looking at the supernode. So here, because of the polarity, that minus sign, that means this voltage must be smaller than that one. So if I take VB and I go up that way to V naught must be bigger by 25 volts, which means I can write down the equation that V naught is VB plus 25 volts. This is equation 5. Now, one thing that I really want to highlight is here we have one equation, two equations. We have two unknowns. We have two equations, two unknowns. We can solve equations 4 and 5. Right. Now, if we go back to the original equations that we had over here, right, notice that this one included a separate variable, this I of 25. Right. Now, if I take equation 2 and I add it to equation 3, so I'm going to take these two equations and add them. And I'm going to do this kind of off to the side. Right. Notice that one of the things that's going to happen is this plus I of 25 and this minus I of 25, when I add them directly together, they're going to cancel out. So here, if I add, and I'm going to do this as scratch work, I'm going to add equations 2 and 3. Right. So I'll have the 2 plus V naught over 50 plus I of 25 volts, followed by VB of 150 plus VB over 20 plus 55, and then minus I of 25 volts, and then 0 plus 0. Right. Notice that this term and that term are going to cancel. This cancels out to 0 as well. And what we're left with is 2 plus V naught over 50 plus VB over 150 plus VB over 20 plus 55, and that's equal to 0. And if you compare this equation mathematically to equation number 4, this one, notice that they're identical. They are exactly the same equation. They contain the same equation, the same information. That means that this other method, where we actually define this variable so that we can keep on going with the node voltage method, we can avoid it altogether by defining the supernode. Right? It leads us to a smaller system of equations. Now, the system of equations I'm going to get from the supernode one. So our system of equations is equation 4 and 5. So here we have VB over 75 plus VB over 150 plus V naught over 50 plus 2 equals 0. And then equation 5 is V naught is equal to VB plus 25. This is our system. This is not in standard form. But we can use a calculator. And one of the things that you will find as you use that calculator is that V naught, which is what we were looking for, is negative 37.5. So I'll leave the rest of those details to you guys. But this was the very thing that we were looking for. And as a bonus, VB, if you wanted to get it, could be very easily obtained by using this equation. Just literally directly plugging in, if you want to do so. All right, this will take care of the supernode. Thanks for watching, and then we'll continue talking about other methods of circuit analysis. In particular, the next section is on a new method.